That is okay, I think we can record. Huh?
That's perfect. Yeah, absolutely.
Okay. Yeah. So welcome everyone to the lattice field theory seminar at ISAR Mohali. So our speaker today is Dr. Jonathan Schock from Cape Town University in South Africa. Jonathan got his PhD in physics from Southampton University in 2005. So Professor Nick Evans was the advisor. So after that, Jonathan did several postdocs. The first one was in Beijing at Institute for Theoretical Physics. Then after that, he moved to Santiago de Compostela University in Spain. Then after that, Max Planck Institute in Munich. Then moved to Cape Town in 2013. So there he's a senior lecturer at the moment. So Jonathan works on mostly theoretical physics. He's also working on string theory, and on top of that, he's doing neuroscience research. So today, Jonathan is going to talk about a guided tour through the landscape of reinforcement learning. So Jonathan, please start.
Great. Thank you very much. Thank you for the invitation. I hope that someday I can actually be there in person. That would be very nice. But for now, this will do. So this is going to be hopefully not very cognitively taxing talk for you, so you can relax. But hopefully it's going to be interesting as well. And I'm going to talk about this topic of reinforcement learning. And it's probably one of the areas of machine learning which is sort of taught less, discussed less, but is actually an extremely important area. So the first question I want to ask you is, why are you here? Why are you at this talk at the moment? And I hope the answer is that there is some value that you see in being here. You know, you want to learn something, and you want to learn something because it can somehow extend your understanding of the world around you, can make you a more intelligent and well-rounded person. It might be that sitting at a talk gives you happiness. And when you are happier, you work better. But the point is that I hope that being here adds some value to you. And I'm not just saying that because I'm giving this talk. I'm saying that because that's actually exactly what reinforcement learning is about. It's about understanding the value of the states that we're in and realizing that the way that we navigate through the world is by finding states which have, in some sense, and I'll define it later, high value. So that's really how you interact with the world. You make choices, and those choices are the ones which you hope, either consciously or subconsciously, will add value to your life. Oh dear. Oh, okay. So the plan for this talk, I'll tell you a little bit about where reinforcement learning fits into AI as a whole. I'll first, after that, talk about what reinforcement learning can actually do before telling you about the mechanics of it, and then give you sort of the basic idea. And the language of reinforcement learning is going to be that of a Markov decision process. And from looking at the Markov decision process, we'll be able to really go into what reinforcement learning is, technically speaking. So the real question is, how do we learn in an environment? And there are a number of exact methods that we can use, things like value iteration. And then we'll talk about Monte Carlo methods, Q-learning. I'll talk a little bit about how neural networks fit into reinforcement learning, in particular deep Q-learning. There's some problems with reinforcement learning, that is, problems that are very hard to solve within the reinforcement learning context, and then some points about the future. So as reference, there's a book by Sutton and Bartow called Reinforcement Learning, and it's really the Bible of the subject. It's an extremely well-written book. They put it out for free online, and it's the sort of book you can read in bed, and it's a wonderful, very fluent read. The RL Bootcamp on YouTube is well worth looking at, and then 2 Minute Papers, if you haven't seen this channel, they put up very, very short overviews of some recent research in machine learning, which is it's a lovely channel. So where does reinforcement learning fit into machine learning as a whole? So I can see my cursor. So we have here artificial intelligence, and within artificial intelligence is machine learning. And the way that I've drawn it here, it actually shows that there are some things which are artificial intelligence, but are not machine learning. And actually, the way artificial intelligence started off was not in the sort of machine learning realm, but was in the realm of formal logic systems and expert systems, where essentially things were hard-coded. And so it might be a set of rules were hard-coded in and output some response. And this is seen as an artificial intelligence system, but it's not a machine learning either by exploring in some environment or exploring from data. So machine learning is the application of artificial intelligence to data such that the machine can learn by itself. So there are really three branches of machine learning. So there's supervised learning, and supervised learning might be something as simple as linear regression. It might be something as complicated as image recognition. So this, the Galaxy Zoo project was to, I'm hearing something from somebody. No, everyone, okay, perfect. So yeah, it might be some sort of complex image recognition where essentially you give it a set of data, and that might be images of galaxies, and it learns to categorize or classify the galaxies. Within unsupervised learning, we have things like finding clusters in data. So you might give the machine some set of data, you don't give it any labels, and that's very important. And it will find that there are certain types of certain regions of this data which it can cluster together. So it might be that you give these data points on the right, and it realizes that here is a cluster. You don't label them as red, green, and blue. It realizes there is some cluster here, there's another one here, and there's another one here. And so things like k-means clustering is the method for that. And then I've got a picture up here of GANs, so generative adversarial networks, which are another form of unsupervised learning and incredibly powerful. And then we've got reinforcement learning, which I'm going to talk about in detail. And then amongst these supervised learning, unsupervised learning, and reinforcement learning, there's this idea of deep learning, which is the application of deep neural nets to these three topics, which just means that you can do much more powerful things than you can without a deep neural network. So reinforcement learning came about from a combination of two disciplines. So one of them is psychology, and oh yes, yeah.
Good afternoon. This is Pata. Hi.
Hi there.
So this previous slide of yours.
Yeah.
As we go inside, is there a computational cost as well as a memory cost increase?
So I don't think it's sort of something linear, but certainly generally you would apply deep learning to data sets which are much bigger and potentially much higher dimensional. So yeah, generally there's going to be a much larger memory cost. I mean, certainly the data that you need to train GANs, you need a lot of data for training something like this. And so the computational costs and the memory costs are both large, but I don't think one can say that it's sort of a some monotonically increasing function from non-deep learning into deep learning. You know, you could do something like linear regression on an enormous data set, which might actually be a relatively large computational cost. But here it's probably going to be some polynomial increase in the number of points that you're looking at. Whereas you might have something which is much harder than a polynomial increase for something that you want to apply deep learning to.
Yeah, thank you.
Sure. So, as I say, reinforcement learning came about from these two disciplines. So one is psychology, and it's simply the idea of asking the question, how do we and other animals behave in the world? And the answer is that we do a lot of trial and error learning. So we experiment with our interactions in the world. We try to do some task. Sometimes it fails, sometimes it doesn't fail. And by correlating the things that we do with the failure or otherwise, we realize the things that we need to do in order to solve the task. And the idea of secondary reinforcers is very important, and I'm going to explain that in a little bit more detail later. But essentially, it's something which we realize leads to successfully performing the task, but isn't itself necessarily an important part of the task. And I'll talk about that later. And then on the computational side, there's this idea of optimal control theory. And within optimal control theory, there are these ideas of value functions and dynamic program, which I'm going to talk about later. This isn't quite learning in the sense of sort of trial and error learning, that I'm going to talk about in a bit. But when you put these two together, you end up essentially with the idea of reinforcement learning. Of course, one then needs to put on a lot of other mathematics to actually make it work, but it's the idea of taking these two concepts of psychological trial and error learning and optimal control theory, and what you get out is reinforcement learning. So I'm going to give you some examples of what reinforcement learning can do. So first of all, this is Google DeepMind using something called the DeepQ network, playing one of the old Atari games. And the idea is that you get the computer to play this game by trial and error. It is able to, its actions are to move something left and right, the paddle at the bottom left and right. And it gets the pixel values from the screen, and it gets, as a reward input, I'll talk about that later, the values at the top. And you want it to increase the score that it can get. And it starts off doing really badly. So it's moving all over the place, and occasionally it manages to hit the ball, and the ball hits one of the bricks, and the bricks breaks, and it realizes that that's a good thing to do. And after a couple of hours, it can play like an expert player. So you can see essentially here it's not making mistakes, it's managing to break through the wall. And actually the rather wonderful thing is that if you let it run for long enough, it'll find that there's actually some somewhat more advanced technique which allows it to play this game even better than most humans would be able to play it. So in fact, it realizes that there's a sort of, not a bug in the system, but there's a shortcut, which is that if it can break up in that top left, as we'll see in a moment, it can let the ball bounce around at the top and increase its score much, much faster. So I don't know how many of you saw the Go competition between Lee Sedol and DeepMind. So this was a program called AlphaGo, which Google DeepMind developed, and essentially it was the first really powerful computational system that could play Go. So Go is an East Asian game which is played a lot in China and Japan and Korea. And it had been thought for a long time that this was beyond the realms of what we would be able to get computers to beat humans at. So chess had been not solved, but chess engines are much more powerful than human players and have been for some time. But the combinatorial difficulty in Go is much, much, much higher than chess. And so it was thought that one could never get a computer to do this. But it turned out that, I guess this was about 3 or 4 years ago now, they played this AlphaGo engine, which had learned via reinforcement learning. And the way it had done that had been, first of all, being given around 100,000 games of Go, historical games of Go. And then it played itself again and again and again and again and again, learning rules which led to positive outcomes, those positive outcomes being winning the game. And this famous match with Lee Sedol, humans and expert players believed that the machine could never win, and in fact, it absolutely thrashed Lee Sedol 4 games to 5. And the most important moment in this was actually a move, which I believe is called move 37, which was in game 2 or 3, and it looked like the computer had made a mistake. It looked like the move that it had made was completely bizarre, and everybody thought, it's okay, humans are still better than computers at this. And Lee Sedol came back to the board and had a look and realized that this move, which no human would ever make, looked strange, but was actually brilliant. And it actually opened an entire new avenue of possibilities within this game that he had never seen before. And so what we saw from AlphaGo was something which was genuinely being creative. It was coming up with new solutions which had value. And this was really a kind of turning point in, at least in the public image of what computers could do. And this used a very, very clever reinforcement learning style engine. So in fact, AlphaGo has now been surpassed by AlphaZero and then by MuZero, and they are much, much more powerful than even AlphaGo. So this is another example. So this is getting a simulated person or simulated agent animal to learn to move. And the aim is simply to say, these are the actions which the animal simulation can do. It can move its limbs in certain ways. And it has to learn by trial and error to move. And indeed, if you run it enough times, it does learn to move. And so it can get over obstacles, it can jump. And the important thing is that it doesn't run in the way that you might imagine a human would run, but it has found a solution to this problem. Simply by trial and error, but very importantly, the computer programmers need to give it an aim, and that aim is to get from A to B as quickly as possible. And indeed, sometimes it looks kind of strange doing it, but it does manage it most of the time, not always.
Hello.
Oh, yes.
Yes, so in the previous two slides, we saw that there is some certain learning curve for the reinforcement learning. So can we quantify the time it will be required to become creative or innovate some new things? So given a set of operations I have already being known to humans, what time will it take quantifiably to find out new operations with the reinforcement machine learning?
That's a really good question. I guess part of the issue is that definition of creativity, of coming up with new solutions which have value. If a human hasn't come up with the solution before, then we think of it as creative, and so it seems a little bit subjective. You know, you can give it the actions that it can take, and you can give it the reward structure of the task, and ask it to go. And really, it's a question of, has a human come up with an ingenious solution or not? And so I think it's going to be very, very task dependent. One of the problems with machine learning in general is that we don't really have a good fundamental theory of it. You know, we have a good fundamental theory of statistical physics. We have a good fundamental theory of many areas of physics. We don't, at the moment with machine learning, we're often using heuristics. So we don't know what is going to be exactly the type of architecture which works for a given problem. So the answer, I think, is that no, we have no idea how to predict that for a given problem at the moment. I think we're still in the very, very early stages of really finding out what actually works in these cases. It's a really good question. So within self-driving cars, reinforcement learning can be used. Of course, one has to be careful. You don't want to sort of send a baby reinforcement learning system out onto the road and for it to learn by trial and error, because errors in a car are kind of dangerous. So, you know, you might start in a simulation, and then you might start off in some very, very simple environment, and the car will learn to, by trial and error, to drive in a straight line or to turn around corners. In fact, reinforcement learning isn't used all that much within self-driving cars, but it's certainly a way that one can think that in the future, we could really tune them better and better and better. Within manufacturing as well. So you might want to get a system to produce car parts more and more efficiently. And so there you have a very well-defined task with the aim to improve efficiency. And you give certain constraints as to the way the robots, let's say, can move. And they explore through trial and error to see what is the best solution. And here, hopefully, let's see, we have a really clean example. So this example is called the swing up cart pole, and basically what we have is a little robot on a rail, and the aim is simply to move the weight so that it's balancing vertically upright. And what we see is that the first few tries, it's moving kind of randomly. It doesn't seem to be actually managing to solve the task at all. But sometimes the pole stays more upright than at other times, and it uses the buffer of knowledge that it has about what it did in order to get there to improve its performance. So now we're at about 5 seconds total experience, and still it doesn't seem to be doing very well. We saw that last time that it seemed to swing it up at least momentarily above the horizontal. We'll see here that again, well, in fact, here it seems to be doing something very strange, but at least it does seem to realize that there are ways to move in order to get the pole to be more vertical. And in this case, I think it just takes about 12 seconds of total experience time to be able to actually solve this problem completely. So here we can clearly see that it is spending more time vertically than the previous times. And I'll just go to the very last time. Where I believe, oh, no, it hasn't quite solved it that time, but the next time I promise you it will solve it. I don't want to spend too much time going through that. Okay. So one of the issues is that teaching rules is generally very hard when there are a lot of possible options. So for instance, you could take the example of that swing up cart bowl, and you could program in the exact dynamics, and you could program the system, sort of hard code in exactly what to do in all situations for it to balance the pole. But actually that's going to be a fairly large amount of code that you need to do, and there are going to be lots of edge cases. It's much easier if you give it a set of rules about how to learn and allow the system to learn for itself.
Hello.
So all of the, oh yes, hi.
So I have a question from the previous video you showed. So
Yeah, sure.
let's say we designed a machine and it's completely autonomous, and let's say it has been running for 1 year or so and it's going perfect. Yep. So how sure are we that it will go on forever working perfect and it won't make any mistake? Like,
so like, one can actually oh, sorry, go on.
Yeah, please.
So within the reinforcement learning framework, I'll talk about this a little bit later, there's the idea of exploration versus exploitation. And essentially what that means is when you're exploring, you're doing things that you haven't done before to see if there are better solutions. And exploitation is using the knowledge that you already have to just keep doing what you're doing because you know that it works. And so, for instance, you can have a reinforcement learning agent where at first you wanted to explore the state space and explore the state of possible actions that it can take. And over time to stop exploring and just start exploiting. And so you could have a reinforcement learning agent which explores for a while, finds a really good solution, and then basically you can tell it, okay, don't do any more exploring, just keep doing exactly what you're doing. And then there's no reason to think that it won't keep doing that. Of course, it might be that the hardware, the robot itself, maybe there's some wearing in the joints over the course of a year. And so you might want it to have some slight leeway in exploring so that it changes its actions a little bit because the joints in the system are changing, and so it has to change its actions a bit. But in a perfect world there, you can certainly say, just keep doing what you're doing, and it will do that. Does that answer the question?
So if it's exploring and always exploring, there will be no random fluctuations that will sort of say be a bad solution or something like that.
Exploring or exploiting?
Exploring.
So exploiting is when it keeps. So exploring, oh, so when it's exploring, there can certainly be sort of lots of fluctuations where it can end up doing something terrible, for sure. So you have to put constraints into such a system to say, within, you can explore, but within some finite space. So, if you had a robot, you could tell it that you never wanted to smash into the walls of the area that it's in, but within those constraints, it can do whatever it wants. So as the programmer, you need to put in constraints that are going to keep the system safe. Of course, if it's a simulation, that doesn't matter at all. But yeah, certainly in a robotic system, one has to take that into account.
Okay, thank you.
Sure. So it might seem like this is part of supervised learning. So it's doing something and it's getting some feedback from the environment. But the important point is that it's what's called evaluative feedback. That is to say, the only thing that the environment says to it is, yes, you did a good job, or no, you didn't do a good job. It doesn't say you did a bad job and this is what you should have done. So instructive would be like that. And that's never happening. It's just learning that the thing that it did was good or bad. Okay. So the fundamental language within reinforcement learning is a so-called Markov decision process. And so what we have here is, I can't see my cursor at the moment. So I'm not going to be able to use that now. So we have a set of states here. So we have some system, and there's a set of states, and those states here are the blue circles and the blue squares. So you might have something which starts off in state 0. And then from state 0, there are a number of actions that you can take. So there's action A1, there's action A2, and there's action A3 from state S0. There's a set of rewards. And so those rewards are the black numbers. So for instance, from A1 back, if you do S0 and you perform action A1, then sometimes you're going to end up back at state S0 and you're going to have a reward of -3. So that's something bad. However, if you perform action A1 on state S0, then sometimes you're going to end up in the what's called terminating state, ST1, and you're going to get a reward of +5. So the shaded boxes with numbers in from green to blue, those are the probabilities, which are transition probabilities, which say, if I'm in state S and I perform action A, then what is the probability that I will end up in state S prime? So for instance, if we're in state S0, we perform action A1, then with probability 0.2, we'll end up back in the state that we started in. With probability 0.5, we're going to end up in state S1. And with probability 0.3, we are going to end up in the terminating state ST1. Okay. And you can see the same thing from the other states. So now we're in S1, and we perform action A1, and with some probability, we're going to end up in the terminating state. We're going to get a reward of +5. But with some probability, we're going to end up in the terminating state ST2, and we're going to get a reward of -2. So we probably don't want to do that, but we haven't actually defined what it is that we want to do yet. So we want another layer on top of this. So the Markov decision process is really the dynamics of the system. But the thing that we want to put on top is what's called a probability, a policy. So the policy essentially is, given that I'm in some state, what am I going to do? What's the probability that I'm going to take a particular action? So the policy is labeled by pi, and it's conditional. It says, if I'm in state Sj, what is the probability of me taking action AI? And you could have something which is deterministic, where if I'm in a particular state, I always perform a particular action. Or you can have something which is stochastic, which says that, well, some of the time I'm going to take one action, and some of the time I'm going to take another action. And the idea of reinforcement learning is going to be, how do I find the optimum policy, the best policy, which somehow increases my rewards over time? And that's it. That's really the fundamental idea of reinforcement learning. So the question is, given that you're in some state, what action should you choose? And of course, that depends on the aim. And the thing that we are aiming to do, our aim, is to increase the total reward over time. And in this case, in the example that we see here in the Markov decision process, we're trying to get into one of the terminating states, and we're trying to get the highest reward possible. Well, in fact, I shouldn't actually say that we're trying to get into one of the terminating states. We're just trying to increase to get the highest reward possible. And indeed, it may be that taking the route from S0 to ST1 via action A1 is the thing that gives us the highest reward. But it might be there's some policy which actually tells us that there's a better way of doing it. So this is the reinforcement learning framework. So we have an agent with a policy, and the policy is, what's the probability that I should perform some particular action AT when I'm in the state ST. So what does the agent get? So the agent gets information about the state that they're in, and given that, they look at their policy and they choose some action to take. So here, step 2 here is taking action AT. That action feeds back to the environment, and the environment changes. So it might be that the agent moves a little bit, or it might be that some particular choice is taken, and there is some change in the environment. It updates to some new state ST+1, and some reward, RT+1, is then fed back to the agent along with the new state of the environment. And so it repeats again and again and again. So the environment reacts to the action, and it might react to, there's a question, yes. Hi.
Yes, so these rewards are categorical variables, right?
The rewards, so the rewards are, they're simply real numbers that are fed back from the environment. So it's simply a real number.
Okay. So when emulating the natural process, this reinforcement learning is carrying out, how does this reward thing works? How does the learner decides the amount of reward?
So the learner doesn't decide, so the programmer has to decide the reward structure. So for instance, it might be that in the game, you're trying to get a system to play Go, and the simplest reward structure would be that when it wins a game, it gets a reward of +1, and when it loses a game, it gets a reward of -1, and then it starts again. It might be that you have some reward structure which is where there are multiple rewards throughout. So for instance, with the cart pole problem, it might be that for every second that the pole is vertical, it gets a reward of +1. And for every second that it's below the vertical, it gets a reward of -1. So you might have something like that. And so it's really the job of the coder to work out what is the reward structure. Does that make sense?
Yes, just a follow-up question. So suppose suppose the machine is playing Chinese this Go game, and it has to follow 5 states: S1, S2, S3, S4, S5, and there are different number of actions available to reach from each subsequent state. So based upon the reward system, the machine will choose an action to reach to the next state, right? So it has to evaluate every reward based on all those 5 states.
So actually what we're going to find is that it's not the reward which is important there, but what's called the value. And I'm going to go into a lot of detail about that. So the reward is the aim, the overall aim of what the agent is trying to do. Through the learning process, it will realize that certain states are valuable because in the future they will lead to rewards. And so the whole idea of reinforcement learning is working out the values of states and keeping moving through the most valuable states possible.
Okay, thank you.
Yeah, sure. Okay. So we could ask the question, does the world seem like a Markov decision process? Well, as I'm sure you all know, within a Markov decision process, there's no memory. So once you are in a given state, it doesn't matter how you got there. So there is no sort of memory there. There's no dynamics, which is important for the future transitions, dependent on how you got to the state that you're in. But you could think about moving. So if I'm moving and I'm at a particular position, then clearly the state that I'm in, if I just define the state as the position that I'm in, what's going to happen in the future is dependent on what happened in the past, because that tells me how fast that I'm going. But of course, you can always build in that memory or some state variable which is associated with where you have come from, such that you can make any non-Markov decision process into a Markov decision process. It means that the information in a given state may be much larger. So for instance, if you have the dynamics of some system, the position may not be enough to create a Markov decision process, but a phase space where you have position and velocity may be enough. So you can always adapt a system into a Markov decision process such that memory is stored as state information. The other point about the MDP, the Markov decision process, is that generally the state information tells you everything that there is to know about the state. But of course, a lot of the time when we're moving through the world, we don't know everything. So we might be in some state, but there's a lot of information that we don't have available to us. And this gives you something called a partially observable Markov decision process. So, you might be behind a set of doors and you have to decide which door to open, but you actually don't know what's on the other side. So you don't know the full state of the system. But you can adapt to these so-called POM DPs, such that you can have reinforcement learning systems which act efficiently within them. The world is also continuous, but there are actually continuous state versions of MDPs which are well understood. So the previous question really leads on to this very well. So we need to understand the difference between the reward and the value. So the reward is something which is received by the agent from the environment, and this is coded into the program. It may be deterministic. or stochastic in the sense that if we're in state S and we perform action A, then the state S prime may be different. So we may move into one state or another state, but whichever state we end up in, the environment then feeds back and tells the agent, this is the reward that you get for being in this state. And it may be that a lot of the time the reward is 0. It may be that most of the states that you're in, you don't get any reward at all. So for instance, in the game of Go, most of the moves that you play, there's no reward for being in a particular state. The only reward you ever get is the reward for winning the game. Okay. However, the value of being in a state is something which the agent needs to derive for itself. And the value essentially is related to the total future rewards given a policy. That is to say, if I'm in some particular state, and I have a policy which says, I'm going to do this, and then I'm going to do this, and then I'm going to do this, and then I'm going to do this, I can say what I think the value of my state is based on the expected total returns or total rewards. So the total reward, this G of tau, where tau specifies some path through a Markov decision process, which may or may not be a stochastic path. So it may be that we have to take an expectation value over this, or if everything is deterministic, then we simply add up all of the rewards that we know that we're going to get from past experience. And it may be that there's some horizon. So this sum from t equals 0, that should be r0 plus r2 plus ... plus rh, where h is the future horizon. So it may be that there's some end of the game, or the game may be infinite, and then you have to be a little more careful. But the total reward is simply the sum of all of the rewards through the particular path, where the path is defined by your policy. Okay. So one way to think about value is in terms of so-called psychic secretions, which was Pavlov's name for the way his dog salivated when he rang the bell. So the important point here is that for Pavlov's dog, so Pavlov would ring the bell, and over time, the dog would associate the bell with the food. And to start with, when the dog sees the food, it starts to salivate, natural process. But over time, it actually starts to salivate when Pavlov rings the bell. So what the dog realizes is that while the food itself is the reward, there is some value in the bell because the bell is associated with the food and the food has the reward. And so the dog learns that the bell itself has some value. There's no reward associated with the bell, but there is value associated with the bell because it leads to a future state, which is the state of having food. Okay. So we're going to talk about a very, very simple example of a Markov decision process, and it's called a grid world. It's basically a maze. And in the maze, you start off in the start state, and you have here 2 terminating states given by the green and the red. So if you end up in the green state and you perform any action from the green state, then you get a reward of +1 and the game is finished. If you end up in the red state, then you perform any action on the next move and you get a reward of -1. So the only rewards in this game are +1 and -1. There's no reward associated with any other state. And the aim of the game is to get the most reward possible. So one thing that we might think about, though, is that if we just want to get the most reward possible, then if we start off at the start state, we could move about all over the place for a very, very, very long time and eventually end up at the +1 and we'd get a reward of +1. So that would be our total reward. Or we could go directly there and we would still get a reward of +1. So it would seem that there's nothing here which is trying to get the agent to solve the game as fast as possible. So is there a question there? Nope. I think somebody's mic is on. I'm hearing some sounds there. So yeah, the point here is that if we're just adding up the total rewards, it actually doesn't. The agent doesn't care about how long it takes to get there. So there's a simple way of solving that. So rather than having our sum, our direct sum, R0 plus R2 plus ... again, that should be RH, we can define it with a so-called discount factor. So the discount factor is a number between 0 and 1, and it's called gamma. And we raise it to the teeth power. So for each time step into the future, gamma to the t becomes smaller and smaller and smaller, which means that if we want to increase our total future reward, then we want to get to the high reward states as quickly as possible so that they're not multiplied by a gamma factor, which is raised to some high power. So if we want to increase our expected G of tau, then we want to solve the problem quickly. Okay. So let's actually now come on to exactly what it is that we want to tell the agent to do. What we want is the agent to find a policy, pi, which maximizes the expectation over the total sum of discounted future rewards conditioned on our policy. Okay. So our policy is, if we're in this state, this is the thing that we should do. And so we want to find the policy which maximizes the expected future returns discounted. And in this case, you know, this is a very sort of simple idea, but it might be that you have some stochastic system where there's a policy which itself is stochastic, and there are transition probabilities. So that this can be a relatively complex thing, but this is the aim of reinforcement learning. We simply want to find a policy which maximizes the expectation over discounted future returns. Okay. So the value here, so in fact, this object here is called the value. So the value of being in a state S, given a policy pi, is the expectation value of this future returns conditioned on your policy, such that the state that you start off in, state S0, is your state S. Okay, so I can say, what's the state of being, let's say, in the top left corner? And it's simply the discounted total future returns, the expectation value of the discounted future returns conditioned on the policy that I have. Okay. But this seems to be a bit confusing. So it looks like in order to know the values of your states, you need a policy, and that's true. But your policy is actually going to be to always move to the most valuable states. So the policy itself defines the values. That's what we saw in that last slide, V of pi for some state S. But knowing the value structure of your system tells you what your policy should be. So if I told you what the values of all of the states were, your policy would simply be move to the state which has the highest value from the state that I'm in. So this seems like it's a bit of a paradox. Policy defines value, but value informs policy. So it turns out that there's going to be a way around this. We can solve this problem. So what's the value of each state in this case? Well, if there's no discount, then the value of every single state is +1. Because, for instance, I should say, this is with the perfect policy. So we're going to start off by assuming that we have the perfect policy and then see what we can do about that. So if we had the perfect policy, then any states other than the red states would be states with value +1 if there's no discounting, because we can always get to the green state under the perfect policy, and so the value of every state, which is the expected future returns, is +1. If we have a discount factor of 0.9, the answer is still pretty trivial. What is the value under the optimal policy? Well, the value of being in that green state is actually 0.9, because on the next step, we'll move out of it, we'll get a reward of 1, and it's discounted by the gamma factor. Actually, I think these are all off by a factor of 0.9. That should be 1, and all the others should be 0.9 less. But the point is that the start state here is a product of 0.9s, because in order to get to the reward state, the final state of +1, the green state, you've got to take several steps under the optimum policy to get there. So this is the value of each of these states. And this is still all deterministic. So now let's try something a little harder. Let's try something where the transitions themselves are stochastic. And what that means is that let's say we're in some particular state and we want to move to the right. So our action is, I want to move to the right. So if we're in a system where the transitions are stochastic, then even if I move to the right, some of the time I might do exactly what it is that I want to do. I'll move to the right, and let's say that's with a probability of 0.7. And the probability of moving in all the other directions is 0.1. Okay. So now there's stochastic dynamics in the system. So we can ask, what's the value of being in this state S22? So it's 0.9 times the value of being in all of the other states that we might end up in. So given that the optimum policy is going to be to move to the right, it's 0.7 times the value of the state to the right, 0.1 times the value of the state to the left, plus 0.1 value to the state below it. And it might be that, in fact, there's a probability of 0.1 of ending up back in the same state, so it's 0.1 times the value of state S22. So it seems that to solve this problem, that's just linear algebra. We've got some relationship between the values of all of the states, and it seems like we should be able to solve this. But the problem is that this is the value under a particular policy. And the problem actually comes about because we are trying to maximize this value. Okay. So given some policy, we want to work out what is the value of all of the states. We then want to compare that with another policy to see if our policy is optimal. So the thing that we're trying to do is ask the question, is our policy always taking us to the highest value state accessible from each point? So let's see if we can do this in an iterative fashion. So as we wrote down before, this is the value of being in a particular state given a policy. It's an expectation value. And we can separate off the t=0 part from the t=1 onwards part. So it's simply the reward of moving into state S1 from state S0, having taken action A0, plus this sum. In fact, I've been a little sloppy here. I should have expanded out the expectation, but really this can be written as the expectation over the reward of being in moving into state S1 plus gamma times the value under the policy of being in state S1, given the policy that we're using, and starting in state S0. So this expectation value needs to be expanded out with two probabilities. The first probability is the policy, which is the probability that I'm in state S, that I will take an action A. So there's a probability associated with that. And then there's a transition probability, which comes from the environment, which is what's the probability that I will end up in state S prime, given that I started in state S and I performed action A. And so we can see this, this famous Bellman equation, which relates the value of a particular state given a policy with the values of the other states in the system that we can reach from that state. Was there a question there? No? Okay. What about the Bellman? So the Bellman optimality equation is now about the optimum policy. So the optimum policy is generally denoted pi star. So that says the value of the state given an optimum policy, that is the best policy that is possible, is this sum maximizing over the actions. So that is to say, I'm always going to take the action which takes me to the highest value states. That's always going to be the optimum policy. But the point is that it relates the value of a state under the optimum policy to the value of all of the other states in the system. But the important point, the reason that this isn't simply linear algebra is because you are maximizing over A, and that makes it a much harder problem. So how can we solve this? So we're going to use something called value iteration. So how do we calculate the optimal values? So we're going to start off with this V of 0, and the V of 0 says this is the first guess. And we're going to sort of iterate this again and again and again, and it's going to go from V0 to V1 to V2. And the VK subscript K star is going to be the optimum policy, and we're going to start off with the wrong answer. So the initial guess is that the value of all of the states under the optimum policy is 0, which we know to be wrong, but we're going to iterate this. So what do we do? So on the first iteration, V1 star of S, what we do is to say, for a given state, let's figure out what value we have by moving into the states around us, which have the maximum value, and indeed the maximum reward. So the reward plus gamma times the value. But of course, the value of all of the other states at the moment is 0. So there's no contribution from that, but there will be a contribution from the rewards. So now those states which are next to states where you do get a reward will now have some associated value. All of the other states won't, they'll still be value 0. And now you do this again. You say, given that I'm in some state, what's the maximum value that this state could be? Well, I look around and say, the states that I can get to from here, what's the maximum value state plus the reward of that state? And I'm going to say that the value of the state that I'm in now is found by maximizing over all of those, and you iterate again and again and again. And it does actually converge. And so eventually you'll end up with this truly optimal value, running this over, however many times you want to get as close to convergence as you want. I'm then going to take those values. So I've now calculated the values of all of my states. And now my policy is simply going to be always take the action which takes me to the next most valuable state. So let's look at that as an example. So let's perform this value iteration on grid world. So to start with, we simply put 0 as the value of all states. On the first iteration, we find that there is some value of these two top right and the middle right states, which are coming from the rewards that you can get to from there. So the value on the first iteration of the optimum policy of all states is maximize over A, this sum over S prime, transition probabilities, gamma factor. The V0 stars, of course, are all 0, but there's some reward. And so these two states do get some associated value. On the next iteration, the states that can be reached from them are going to end up with some value. Because, for instance, this 0.63, this comes about because I see now that there is a state next to me that has some value. And so I get a sort of associated value from the probability that I might move into that state if I do the best possible thing. And we can do that again and again and again. And we see that the values sort of propagate back to the start state. And this is the sort of convergent solution. These are the values. So the value of that state next to the one state is a value of 0.8. Remember, that's not a reward. There's no reward associated with that. That value only comes from the fact that in the future, I know that under my optimal policy, I'm going to get a reward of +1. And so now what is the policy? Well, the policy is that we start off in the state 0, 0, and we move to the state with the highest reward, the highest value associated with it, and that's the 0.34 state. Then we move up and right and right and right, and we end up in the final state. And that is the fastest way to get to the reward state within this system. How are we doing for time? Oh gosh.
How do you know that the value doesn't fluctuate along a path, along an optimal path? Is there a theorem that tells you that?
Yes.
I suppose there's I might be deceived that it's better actually to accept going down, and then I'll find a path that goes up.
So you mean, might you find some sort of local optimum?
Yeah, well, I mean, you see, for instance, in your diagram, the right path to the right always leads to lower values. But
yes,
I mean, I could imagine that I start off with going to a lower value, but then I find a path connected to that value which goes to the higher value, something like.
Sure. So one can actually prove that this is convergent on the optimal solution. So if you run this enough times, you should always end up in a situation where you will always be taking the route which has the highest value.
By making only local decisions, that means at any point you would decide which is the direction with the highest value.
That's correct.
Get an increase in value, and I'll keep following that, and I'll always land up there. That
exactly.
Sort of exactly. The topography of your decision tree or whatever. I mean, it's a landscape, right? That is
sure.
very
Yeah.
There are no deceptive saddle points or anything like that.
So from what I remember, so it's actually it's explained in the book Sutton and Bartow. This is a convergent algorithm, and I think it's to do with the fact that apart from the maximization over A, this is a linear problem. So apart from having to maximize over the actions, this is linear, and so you can actually prove that there will always be some optimal path, and value iteration will converge on the optimal path.
Okay, thank you.
It's a very good question, and I think my answer isn't a very technical one, but I believe the answer is that it is genuinely convergent to the optimum path using value iteration.
I have a very naive question. So why is this red
Please.
box crossed out? Why is that
Sorry.
quantification not allowed?
No, perfect. It's not a naive question at all. I didn't explain it. So one can define the grid world however you want, and I just happen to have defined it such that there's a state in the middle which you're not allowed to go into. So that's it. So you can define a grid world with all sorts of obstacles and different reward structures. I've just defined one here where there's a state that you can never get into. It's impossible to get into it. And then there are these two rewards of +1 and -1. It's a good question.
Okay, thanks.
Sure. So I know that I'm going rather slowly. So I guess, how long do I have, Anosh?
So maybe 5 to 10 minutes. Is that okay?
Okay. Yeah, perfect. I don't know if I can finish, but we'll see if we can get to. So what did we need to know in order to do this? Well, what we actually needed was to have an explicit knowledge of the model. So we needed to know the transition probabilities exactly in order to do that. And we needed to know the reward structure. And sometimes we don't have that information. So what we need to do is to sample from the environment. So it turns out that these sorts of methods that I've talked about so far, so this value iteration, and there's another version called policy iteration, which is quite similar. So these are actually relatively efficient for a given Markov decision process. The problem is that if you have a system where there's a huge number of states, these methods are completely impractical, because you need to, for these methods, you need to take into account every state that you can be in. And so if, for instance, you're playing Tetris, well, there's about 10 to the 60 states, and so that's clearly completely impractical. So these dynamic programming methods are not going to work. So what we could actually do rather than value iteration or policy iteration is a simple Monte Carlo. So in order to do that, we're going to adapt our notion of a state value to what's called a state action value. So the state value was what is the value of being in this state S? And that's associated with the values of moving into other states and future reward. The state action value is what is the value of being in this state and taking this action, okay? And it turns out that we can use Monte Carlo methods using this language, and we don't need to know the underlying dynamics of the environment. So the environment will simply feed back the information to us about what new state we're in and what the reward is. We don't need to know the transition probabilities themselves. Okay. So just quickly, we're going to write down the so-called Bellman equation for the state action values. So, oh, I'm not hearing very clearly there. Nope. Okay. So the Bellman equation for the state action value, so Q here is the value of being in state S, taking action A under the optimum policy, and it's very similar to the previous Bellman equation, but rather than having plus gamma times the value of being in the next state, you are maximizing over the actions of this optimum Q value. So we see the difference between these two. So it turns out that the V may require less memory, but you need an extra step in the calculation of the policy because you need to work out which is the action which will get you to the next most valuable state. So Q here now, there are 4 Q values for each state. So it's associated with the state that you're in and the action that you can take. So what are we going to do for the Monte Carlo method? Well, we'll start off in some state S, and we will follow the policy pi. So we define some policy, and it might be a completely random policy, and we simply follow that policy, and we calculate all of the future rewards. So we're not having to calculate what happens in terms of the future values. We just have to calculate what's the reward that we get from the environment, starting in the state S, taking this first action A, and then following the policy. And discounting, which takes into account how long it takes to get a reward, we're then going to feed that back and say that, well, this is the value Q of pi of S and A. So there's a bit of a problem with this, which is that if the policy is deterministic, and let's say the transition probabilities are deterministic, then we're only going to ever take one path given a policy pi, and so we're not actually going to learn about we're not going to get much information from that one path. So we can understand, we can improve that by doing the same thing for every state action pair. And of course, again, if you're in something like Tetris, that's going to be a huge calculation, and there are going to be ways around that. But essentially, all we do is we say, we're going to start off in this state, we're going to take this action, and in order to calculate the value of the state action pair under a policy, we're just going to follow the policy, and then if we get reward, we're going to feed that back, and that's going to update our knowledge about how valuable this state action pair is. So what we would do here is we would start off with some policy, pi 0. We would explore using different starts and different actions. That's going to give us information about the Q values. We're then going to define the Q values that we found through this Monte Carlo exploration, and we're going to give that Q pi 0. And we're then going to improve the policy. We're going to say, okay, now given that I know these new Q values, what would the optimum policy be based on those Q values? And that gives us policy pi 1. I'm then going to explore again, given this policy pi 1, and that's going to give me a new set of Q values. And we do that again and again and again, using what's called a greedy policy. So a greedy policy is to say, the policy is going to be always take the action which maximizes the Q value. Okay? And it turns out that, again, doing this is actually convergent. And so we end up with an optimum set of Q values and an optimum policy. Let's see, sorry. So with this Monte Carlo exploration, you've got to take a lot of steps. So it might be that we start off in all of these different states and we take lots of steps and then we feed the information back. It turns out that there's a simpler way to do that. Rather than taking lots of steps into the future, we might just take one step into the future and feed that information back. And these types of methods are called temporal difference learning methods. So SASA, which is a particular temporal difference learning method. So we start off with some arbitrary set of Q for all of the S's and A's. We choose some initial state, S. We choose an action using the epsilon greedy Q value. And what that actually means is that most of the time, we are going to choose the action which maximizes Q of S of A. And some of the time, with probability epsilon, we won't, just so that we can do some exploration. We take that action, we're going to move into some new state S prime, and we're going to get a reward based on it. The target of the S prime is going to be the reward plus gamma times the Q value that we had for that new state S prime, and A prime, which is based on the policy that we have. And we're going to back propagate that information to the previous state that we were in to say, we've just found out some new information. And we're going to change its value by using a weighted sum alpha with some weight alpha based on the new information that we found, weighted with the information that we previously had. So the way to think about this, I'm in some state. I think I know what the Q value of being in this state and taking this action A is. So I've got some value that I think it is. I take the action, the environment gives me back some reward, and that updates my information. It might be that it's very surprising. It might be that I get some very high reward for being in that state. And I'm going to update the Q value of that previous state based on the new information that I have. And it turns out that you can repeat this over and over again. You don't need to do this Monte Carlo search way into the future. You can just update the Q values based on a single step into the future, and you iterate. And again, this is a convergent algorithm. Q learning is essentially the same thing, but rather than using the policy to define the target, we always take the action which maximizes the Q value for being in the next state. So I realized that I'm going rather slower than I'd hoped. So Essentially, the Q-learning is one of the fundamental algorithms for reinforcement learning, which allows you to calculate the state action value pairs for a given system by exploring a single step into the future, taking information about the reward and propagating it back. You don't need to know anything about the transition probabilities because the environment tells you where you've gone to, and you can use this to calculate the policy. So generally in a system where you've got lots of states, this is not going to be an efficient way to do it. So I'm not going to go through this in any detail, but essentially one can use a neural network to have some approximation of the Q value. So you've got some set of parameters, which might be the weights of your neural network. So you've got Q, which is parameterized by theta, and there are ways that you can use backpropagation to update the weights of your neural network such that you optimize your Q value. I'm not going to go into the details of that. In fact, given the time, I'm going to move just onto the last two slides. So some of the problems with reinforcement learning are something called the long-term credit assignment problem. And essentially that is to say, it might be that I only get some reward way into the future. So how am I supposed to learn about what I should do in some local region if I don't get any feedback until way into the future? And the answer is that one way to do it is to use something called curiosity-driven reinforcement learning, where there's some intrinsic reward for the system, which is that it is rewarded for being curious. That is to say, it's rewarded explicitly for moving into states that it has never explored before. And it turns out that certain games like Montezuma's Revenge, which are really, really hard generally, using curiosity-driven reinforcement learning, using something called random network distillation, it actually turns out that you can solve a game like this, or at least do very well in the game. Another question you might have is, if you've learned in some environment, can you take information from that and transfer it into some new environment? So it might be that you get a reinforcement learning agent to play some game, and it gets very good at playing that game. And then you give it a new game, and basically it has to start from scratch. And so a really important question is, how do you do knowledge transfer within reinforcement learning? One way to think about many of these problems actually is to use world models, where a world model is that the agent simulates itself some idea of the environment. And so it doesn't actually need to use the environment. It's got some simulated version of the environment, and it can learn from its simulated world model. Some recent advances in reinforcement learning. So actually this is now a couple of years ago, but if you go online and look for the videos of OpenAI's Dota 2 engine, it was able to beat the world champions at this incredibly complicated multiplayer game. So that's worth having a look at. So finally, if you have a task where you can define some reward function, a reinforcement agent has a really good chance of being able to learn how to perform the tasks, given certain issues associated with long-term credit assignment and transfer learning and all of these sorts of things. A combination of using reinforcement learning with deep neural networks is incredibly powerful. So things like AlphaGo was based on a number of different neural networks which model different parts of the reinforcement learning space. It used something related to an actor-critic method. There are many different extensions to the things that I've discussed. Multi-agent reinforcement learning, world models, causal reasoning. So it might be that you want your agent to have some sort of causal reasoning of the environment that it's in. The active inference framework is a very, very interesting framework that one can sort of put on top of the reinforcement learning picture. And there are many different reinforcement learning algorithms that I have spoken about here. So I'm sorry for being a few minutes over time there, but I'm going to stop there. I'm very happy to clear up any questions if you have them.
Yes, I have a question.
Sure.
So can I imitate the principle of least action using some policy? So suppose I am doing some physics of a system where I have written down the Lagrangian analytically, but it is very hard for me to find out the equation of motion. So I want some system to find out the optimal path for the particle. So can I use reinforcement learning there?
Yeah, absolutely. So there you could define a reward structure based on, let's say, minimizing the energy of the system, trying to get the system to move into lowest energy states. And so as long as you define the reward structure properly, you can get an agent to perform some dynamics, which always minimizes the energy, which essentially is going to give you the same solution as solving the dynamics of the system. Yeah.
Okay.
More questions?
So very often, actually, one of the main issues is how do you define the reward function properly? Defining the reward function in the right way is really key, because you can, it might be that you give it some, well, in fact, here's a good example. In quite a few games, if you just use the score as the reward function, then very often the agent will find a bug in the game and solve the game in a way that you didn't want it to at all, because it realizes that there's some shortcut. And so you have to be very careful that it's not going to find a fault in your system and find a shortcut to solving the problem, because you haven't either defined the environment properly or defined the reward function in the way that you actually want it to.
John, maybe I can ask a question. So could we use these ideas to learn a manifold?
You mean essentially to learn a manifold in what sense?
Generally speaking, we have some data points on the manifold, but we don't know exactly what this manifold is. So is it possible to, simplest case, we can take a sphere, okay? So say we have some data points on the sphere, and using these data points, is it possible to reconstruct? I mean, using some of the data points.
So I would say that reinforcement learning probably wouldn't be the best way to solve that sort of problem within the machine learning context. I mean, essentially, you have a well-defined least squares problem. So you can parameterize your set of possible manifolds. Let's say, let's say you have a family of ellipsoids, and you can define a least squares function, and then you can just do gradient descent to find the minimal solution there, or the optimal solution. So I would say that reinforcement learning would probably be overkill in a case like that.
Oh, I see. So what would be the best, method? I mean, in the literature, what is the name for this? Which aspect of?
Yeah, I would say that would be gradient descent on a loss function, where the loss function is just the least squares between the manifold that you think might be the best solution and the set of points.
I see.
I have maybe a naive question. Often one tries to find a solution of some very nonlinear set of equations using something like the Nelder-Mead amoeba method, where you form the simplex in the parameter space, and then the amoeba moves through this space trying to capture a point where essentially this chi-squared function minimizes, where and you often get stuck in local minima, and then you try to restart the system and keep searching. Do these new methods allow you to hope that you can do much better than that?
So very often
equations are not a question of learning the nature of a data set, or but just given some nonlinear mathematical equations that you need to solve. I guess this question was asked earlier also in some form, but I just want to know, ask it again. Can you do better?
Yeah, that's a good question. So I don't know about these methods. I could imagine if you have sort of some amoeba moving through the simplex, and there's some associated behavior of this agent essentially moving through it.
No, the amoeba is the simplex. That you start with the simplex, and the simplex deforms itself. It's actually the most standard multivariable search method. Nelder and Mead.
Okay.
They're in Press-Tucholsky and so on as the most powerful method available for a very non-linear system. If you want to find a solution.
Sure. So yeah, I mean, one could certainly think about using a reinforcement learning algorithm in that case, where you have a well-defined error, which can itself give you a well-defined reward. So your reward again might be associated with minimizing this error, and you've got some set of actions, which is the changes in the simplex shape. So you could use something like an epsilon greedy, where it's going to try to keep doing the thing that it's doing because it knows that that is generally a good thing to do, but every now and then it changes its behavior, which helps you to jump out of local minimum.
Yeah, the problem in that kind of system is typically that there are a very large number of local minima, and it's very, you land up even with 50 variables or something, you'd land up spending huge amounts of time trying to, and a very non-linear system, like a large system of non-linear matrix equations or something like that.
Sorry, go on.
Okay.
Well, my guess would be that actually something like a genetic algorithm may be a better way than a reinforcement learning algorithm to help with a problem like that.
Okay, thank you.
Sure.
Any other questions?
So I have a question. So probably this question of steepest descent method was asked. So I was wondering if the whole configuration space is not being explored, then how can one really comment on the steepest descent method, or even comment on assigning weights to different paths, or say?
So with the original methods that I spoke about, so this value and policy iteration, essentially you do need to take into account the entire state space in order to do that. And of course, that's very difficult in a very high dimensional state space. So you don't use those methods. The point is that if you're using something like Q-learning and you're not exploring every state, then you can certainly end up in local minima. So it's unlikely so for instance, when in the game of Go, although people have used reinforcement learning to create agents which are much, much, much better than humans, it's clear that the solutions that the agent has found are only local minima. So if it wasn't a local minimum, then it would have solved Go, and Go certainly hasn't been solved. That is to say that we know that there are likely to be much, much better policies which take much more complex routes in the phase space. All we've managed to do is to find routes which are much better than those that humans have managed to find.
Yes.
I don't know if that answers the question at all.
Okay, yes, that does. So I was thinking about in the context of Lefschetz thimble, let's say, because in that case, so it is very difficult to consider find out the weights if more than one or thimble is contributing to the observable. So something like that, yeah.
I'm not sure I know that example.
Okay. So maybe the first one which I asked probably answers that. Yeah, thanks.
Okay, sure.
More questions? So it seems like there are no more questions. So let's thank Jonathan for a nice talk. So yeah, thank you, John.
Pleasure.
So we hope to have you here at some point at ISER Mohali when things are back to normal.
For sure. I would love to. Thank you very much. Wonderful. Thank you.
So I guess that's it. So yeah, thank you all. So